What's going on, YouTube? Welcome back to the System Design Series, a comprehensive deep dive. And today we are going to talk about load balancers. Now, load balancers are a very vital component of any distributed systems. And you might be wondering, if you've never heard of them, what are load balancers and what do they do? We're going to explain that right here in a second. Now, load balancers, what they do is they help spread traffic across a cluster of servers to improve the responsiveness and availability of applications and websites, right? So they help evenly distribute traffic across a cluster of servers, and they keep track and they monitor the health and the status of all the other resources while distributing these requests. And if one of those servers isn't healthy or responding correctly, a load balancer would stop sending requests to that particular server. So you could just think of them as a reverse proxy that sits between clients and the servers and acts on behalf of those servers, right? So typically, like I said, a load balancer sits between a client and a server, accepting like all the incoming network and application traffic and distributing them across multiple backend servers using various sorts of little intricate algorithms, which we'll talk about later. So when they balance these requests across these servers, a load balancer reduces the individual server load and prevents one of these application servers from becoming a single point of failure. Thus, all this improves the availability and the responsiveness of a system. And here's a very simple diagram. We have the clients on the left. They make some sort of request, and a DNS lookup is forwarded to a load balancer, which is basically a server that distributes traffic. And it sees all these requests and it evenly distributes it to these servers. And there's various ways in which it does that, and we're going to talk about that a little bit. And like I said before, if you want to really utilize the full scalability and redundancy of these load balancers, we can try and balance load at each level of a system, right? And you can have them in a few places. We see one here between a client and a web server. And this little symbol here, this N plus symbol, not to confuse you, is just the logo for a very popular type of load balancer, software load balancer, Nginx, which you'll probably see or hear of in the wild. There's others, but we'll discuss that later, like I said. For now, just know that it can be in between different layers of your application. Here, it's between the client and the web server. You can also have them between the web servers and the internal platform layer, like your application servers here and your cache servers. And you can have them between your internal platform layer here and your database. And what this does is just all this traffic that's coming between these different components, it just evenly distributes it. So it doesn't just have to be between a client and a web server. It can be between multiple layers. So what are the benefits of load balancing? We have a few. We have a lot actually, but I'm going to name a few here in this video. So one of them is users experience much faster uninterrupted service. And that's because traffic is just being spread over multiple servers instead of overloading one. So you, the end user, you're experiencing much faster service that's uninterrupted. Like I said, if one of those servers decides to just quit, the load balancer is just going to stop sending traffic to that. And there's other intricacies that can happen on the back end, like another server can be instantiated in place of that one, or like the load balancer is just going to send it to another server which isn't handling as much traffic, right? Another benefit to load balancing is service providers experience less downtime and higher throughput. So users won't even experience the failure. Traffic, like I said, is just rerouted to a healthy server. And smart software load balancers, they have tools that provide predictive analytics that iron out all the traffic bottlenecks before they even happen. So your analytics tool can say, hey, man, there might be a bottleneck that's going to happen at server A because server A is handling a lot of requests right now. So let me send it to like server B or C or D, whichever server isn't handling as many requests right now, and just to evenly distribute that traffic, right? And another benefit, and this is for system administrators, They experience fewer failed stress components, and there's less of that hassle for them to deal with because multiple servers are performing smaller chunks of work versus one server performing massive amounts of traffic and requests, right? And there's different types of load balancers. Like I said, there's your software and there's your hardware load balancers. And on the left, you'll see the hardware load balancers. Now, hardware load balancers are actual machines, you know, they're actual machines. And, you've probably seen them in like movies, a room with like the glass and the hacker comes in and you see all this stuff right here on the left. You see the wires and the cable. Some of those are servers and some of those are load balancers, right? And, they're actually very expensive and they're limited in their configuration and flexibility. And you don't really need to know too much about them for the context of like system design and system design interviews. But nonetheless, they're still good to know about or just know that they exist. And some of the top or more common hardware load balancers that you see includes the one on the left, like the TP-Link, the F5, and Barracuda. If you want to go research those on your own, you can, but like I said, that's beyond the scope of this video. On the right is software load balancers. We have software load balancers, which you'll more commonly see in the wild in applications. You have Nginx, like I said. You have Neutrino, HAProxy, and ZevNet. And each one of them are good at particular things versus the other, right? Kind of think of it as SQL. SQL has multiple different flavors, but some flavors of SQL are better at some specific things than others. Some are better at stored procedures, or some are better at this or that. The point I'm trying to get at is there's advantages depending on the use and a type of application you're building or you're working on, whether it's a read heavy application, write heavy application. There's going to be load balancers that are better suited for your particular type of application. Here's a few. You have HAProxy, ZevNet, Nginx, Neutrino, like I said. You can just go research that on your own time. Again, like I said, they are beyond the scope of this video, but it's good to know that they exist. Now, I mentioned different types of load balancing algorithms that help distribute traffic amongst the backend servers. Now, one of the more famous and more widely used algorithms is the round robin approach. And what that does is it takes a bunch of requests and just evenly distributes them amongst the servers in a sequential order. So it can go from like top down from this server here, so on and so forth, or bottom up from the bottom, this last one to this one to that one to this one to the top one. As long as it follows some sort of sequence that is consistent, that's what a round robin does. It distributes, like, let's say this is 10,000 requests. It's going to start here, 2,000 here, 2,000 here, 2,000 here, 2,000 here, 2,000 here, and so on and so forth, and go the next 10,000 and 2,000 here, 2,000 here, 2,000 here, 2,000 here. And as long as it follows a consistent sequence in order in which it evenly distributes that traffic, that's like what a round robin does, right? And there's another type of round robin, which is a weighted round robin, and pretty much it's the same thing, aside from one minor difference. You see that big server in the middle with the X's over it, the blue X's, kind of bigger than the others. What that is this server is more powerful, can compute more, and it's just like a more powerful server than these other servers, and it might be used for processing or handling things like video or other types of resources. But the crux of what they do is what a weighted round robin is you have scheduling that is designed to better handle servers with different processing capacities. So each server is assigned a weight, and that's usually an integer value that indicates the processing capacity. And the servers with the higher weights receive new connections before those with less weights. and the servers with higher weight get more connections than those with less weight. So what that basically means is that the servers that are more suited for handling, that are just more powerful, they have like a weighted, so this one is weighted, and it's put above all the other servers being more powerful. So more traffic is sent to that one. You also have the least connection and the least response time method. And what the least connection method does is it directs traffic to servers with the fewest active connection. And all that means is, you see this orange asterisk here near this server. Let's just say these other servers have 20,000 connections or 20,000 requests apiece, right? And this one only has 5,000. What the load balancer is going to do is, the next bunch of requests, it's going to look at all these other all these other servers and say, hey, this server here with the asterisk only has a few thousand requests. These other ones have 20,000. This one might have only 2 or 5,000. Let me send the next bunch of requests here so I can more evenly distribute these the load that each one of these servers has, right? And the least response time method is similar to that, in that it directs traffic to servers with the fewest active connections and the lowest average response time, which basically means, if this server here has, fewer active connections and a lower response time, send it here. That's really just a minute difference. Next, we have IP hashing, which is basically assigning a unique hash key to a source IP address to route non-sticky traffic to some backend server. And the load balancer just routes the same request from the same client to some backend server, as long as that server is available. So what does that mean? Because I'm just reading the notes that I just jotted down here, and I want to simplify this as much as possible. This load balancer here is going to see a request from this specific client, which has this IP address. And what it does, and I don't think this is really how it hashes. You don't have to know how it hashes. I just wanted to create like a visual representation, and I just made up some goobly gop to put up here. I don't know, but you don't have to worry too much about this. What it does is it takes this IP address and it hashes it, and that hash is going to correlate to some specific server. And if you already have caching implemented in your system, and the response that client already made is cached in that particular server, it's just going to send it back to that client. So what does that mean? It means that this client is going to correspond to a specific backend server, because the load balancer hashes their IP address and assigns their IP address to some particular server, as long as that server is still available. And it might be, the client might be making the same request, or have requested that same resource in the past, and it already might be cached in this server, so it just sends that response to that client. And that's basically what IP hashing is in a nutshell. Next, we're going to talk about redundant load balancers. Now, in system design, above all else, we want to make systems highly reliable and in turn very available, or highly available, reducing the latency and increasing throughput, as well as mitigating single points of failure. Now, a load balancer can be a single point of failure if not implemented in the right way. Thus, we can add more load balancers to create a cluster, and in this cluster, these load balancers are going to be monitoring each other, and each one of these load balancers are going to be equally capable of serving the same amounts of traffic, and detecting whether the other one fails, and whatnot, and so on and so forth, right? So let's just, for an example, say in the wild, you'll see at bigger companies or startups or this, that, and the third, depending on the size of their application and the scale at which their application operates, they're going to have more than 2 load balancers. But this is just a high level bird's eye view, 10,000 foot picture of how this works. So I'm only going to use 2 load balancers to illustrate a point. But basically, these two load balancers in this cluster, this very simple cluster, they're monitoring each other. And this top one is the active one right here, right? And this other passive one is, is not being used. So for whatever reason, this one fails, right? Gonna draw an X through that. That one fails. So since this other passive load balancer is monitoring the health of the other one, it notices, hey, this guy failed. Let me take over. I can handle the same amount of traffic. I'm basically the same machine, just cloned and ready and available in case this other one fails. And that's what it does. It takes over and it starts, directing traffic to the back end servers, and that just gonna reduce the latency, and you won't even notice the system failure happens. This might happen, at an application and you're using in real time. This happens instantaneously. You won't even notice. And that's a good way to design systems, is making clusters of load balancers which are redundant, that can take over if one of them fails. Thanks for tuning in. Make sure you go ahead and subscribe to the channel, and also follow us on both Instagram and Twitter at Ming Tech Media, all one word. All right.